Welcome to Analytic Methods for Lawyers. This lecture is on basic statistics and the foundational idea of a distribution. The idea of statistics is just so important for lawyers these days. An awful lot of modern litigation is about statistics, and certainly your clients are going to be using statistics in a lot of their work. And really, to me, the key to understanding statistics is to understand the concept of a distribution. So this video is going to be about that concept along with things that go with it, such as functions of distributions, conditional distributions, transformations of distributions, and much more. But the hope is that with a good foundation, we'll be able to understand regression, machine learning, and other areas as well. I also want to thank, as we start off, a guy named Roger Germanson, who's a developer and officer at Wolfram Research, and he developed really an architecture for presenting statistics that is just fabulous and makes it much easier to understand, I think, than in other computer languages or, frankly, in an awful lot of text. So thank you, Roger, and if I screwed up, sorry. All right, so let's talk about what is a distribution. And distributions, I think, are more like firms. Um, they are firms that have factories, and those factories produce either numbers or things that correspond to numbers. The firms themselves have names, so you might have the Bernoulli Distribution firm, or the Uniform Distribution firm, or the Normal Distribution firm. And the factories have parameters that describe their relationship to the firm, so that all factories within the firm have a certain number of features in common, but also differ slightly from each other. There are an awful lot of distributions. In fact, I guess there are an infinite number of distributions, but the Wolfram language happens to know about 160 of them, and you can see them listed here, and a lot of these we will just never see, but it's good to know that they're there if you want them. So let's start with what I think is the simplest distribution of all, which is the Bernoulli distribution. And the Bernoulli distribution is basically a coin flip. It produces either a 0 or a 1, although the coin can be biased. It doesn't always have to be 50% heads and 50% tails. So it could be 70% heads or 40% heads, whatever you want. But what the Bernoulli distribution does is it produces zeros and ones. So in Wolfram language, to represent a Bernoulli distribution, you can see the code that we've done, and if I execute it, it's just going to return a Bernoulli distribution. It doesn't know what to do with it yet. We're going to learn what to do with that distribution. For now, it's just kind of sitting there. You can have a symbolic Bernoulli distribution in which you don't pre-specify what the probability of a head is. You simply say it's some parameter, and I use that word precisely, alpha. So there's our Bernoulli distribution with alpha. Maybe later we'll tell the computer what alpha is. Okay, so now we want the distribution to actually do something, and we want it to make products. And the function that has the distribution make products is called random variate. And so what we do is we have two arguments. We have the distribution itself, and then we have how many outputs do we want to see. That's the second argument. So let's produce 100 draws from the Bernoulli distribution firm, and the specific factory is one that produces 70% heads, or really ones. So there we are. If you look at it, it looks like there are about 70% ones. Doesn't mean exactly. We can use the counts function and say count that. Remember, the percentage means what you last outputted. So that came out about right. And you should notice that you have to have a concrete distribution in order to draw random variates. That is, you can have an abstract factory, but when you actually want to make something, you need to specify the parameters. So what I'm about to execute is going to fail. Okay, it doesn't know what to do with it. All right, so that's our friend, the Bernoulli distribution. Let's try something else. Let's try a uniform distribution. And a uniform distribution produces numbers between its bottom parameter and its top parameter, and every number in between has an equal probability of being produced. So we can parameterize it with this pair of numbers. So here 3 to 7, and what this is saying is when you produce something, every number between 3 and 7 should be equally likely to be produced. Again, we can have a symbolic uniform distribution in which we don't specify in advance the parameters. So we could draw 100,000 values from a uniform distribution on the interval 3 to 7. Here's our random variate function to do that. And we could then ask the computer to make a histogram showing how frequently each of these are. And I'm hoping you have a picture in your mind of what you're going to see before I execute the code, which is that since all outcomes are equally likely, the bins of the histogram should be of about equal height. And let's see if that's true. And lo and behold, it is. Um, okay, so um, you should notice that there are other ways of writing a distribution. That is, the parameterization we used for the uniform distribution said that the first number here was the low bound, and the second number here was the upper bound. But you don't have to do it that way. You could say that let's have the first number be the midpoint of the distribution of the outcomes, and the second number be the radius. How far away from that midpoint can you go? And so you can see that I can create a reparameterized uniform distribution simply with this function mean radius uniform distribution. And they're exactly the same. If I do mean radius uniform distribution, is that the same as, that's what equals means, is this the same as this? It's going to say yes. Why? Because if the midpoint is 5 and the radius is 2, then the low point is 5 minus 2, which is 3, and the high point is 5 plus 2, which is 7. So for many distributions, there is sort of a canonical way of parameterizing them that's used all the time. So the normal distribution, for example, is almost always described the same way. But sometimes there are more useful parameterizations of distributions, and we may be seeing some of that in the course. All right. Distributions have domains. That is, these are the outputs that the distribution can produce. Uh, Often that domain is factory specific. That is, the uniform distribution on the interval 3 to 7 cannot produce a 2, whereas the uniform distribution on the interval 0 to 6 can do so. Um, so we can use the function distribution domain to determine what is the domain of a distribution. And here we have the uniform distribution on the interval 1 to 6, and it can produce anything in the interval 1 to 6. Or we can look at a cousin of the uniform distribution called the discrete uniform distribution. Here, when I have 1 to 6, we're basically modeling a die roll in which the outputs are going to be 1, 2, 3, 4, 5, 6. Here's a little different die. This would be a funky, what is this, an 11-sided die that can produce numbers from 2 to 12. I've never seen one of those. Maybe it exists. And you can see that it's producing the domain. Those little semicolons there means span, and that basically means all the integers from the first number 1 to the second number 6, or the first number 2 to the second number 12. Um, so we can, as I think I've mentioned, have multivariate distributions that produce, the factory always produces more than one number at the same time. And so here we have a funny multivariate t distribution. We'll see that later in the course when we look at regressions. And what you'll see is that it produces two numbers, both of which can be any number from negative infinity to infinity. Here's another, and you can see it producing two numbers here. I'm producing using random variate to produce 5 pairs of two numbers. Okay, so that is the notion of a distribution domain. Let's talk about another type of distribution, which is a categorical distribution. And a categorical distribution does not produce necessarily numbers. It can produce anything you want. So here's a categorical distribution that its outputs letters of the alphabet, A, B, C, D, and E. How frequently does it do so? That's determined by the second argument here. And so you might suspect that E's are going to come out of the factory much more than A's. So we'll just evaluate that, name it the distribution. It gives a nice picture since this is actually a complicated object. If I push on that plus button, we get some more information about it. But I can ask, use random variate to produce outputs from the factory the same as I did with the uniform distribution or a Bernoulli distribution. So there we go. It's producing random outputs from the categorical distribution factory. Categorical distributions can also produce multiple values at the same time. You can have a multivariate categorical distribution. Here, it's going to produce a letter from A to E and a number from 5 to 12. And here are various weights that are associated with it. Let's actually just evaluate that right now. I'm going to use Apple return, do an in-place evaluation. Those are the weights that are associated with each possibility. And now we have a categorical distribution, and I can produce some outputs from it using random variates. And this is, D6 and E8 and A7. Maybe you could use this to build a battleship generator if anyone plays Battleship anymore. Okay, so you will hear in other arenas the term random variable, and I think it's a very confusing term because it's not really a variable in the way you think about it. And therefore, I would prefer that we use the notion of a distribution. The two are essentially synonymous. And so if you hear random variable, though, basically they're talking about a distribution from which a random variate is produced. All right, that is the most fundamental idea. I would urge you to re-listen to this part of the video as much as you can possibly tolerate until you have a really good understanding of what a distribution is.
Now that we've seen what a distribution is and realized that it's just sort of a firm or a factory from a firm, let's actually see what one can do with a distribution and look at functions of distributions. So one thing we can do to start off with is just define a distribution that we're going to be using in this discussion. And so let's make it the discrete uniform distribution that runs from 1 to 6. This is a way of emulating a die. The outputs can be 1, 2, 3, 4, 5, 6, and they are uniform in their probabilities. So I can ask some questions about that distribution. I can ask, what's the probability that if you take some value x that's distributed according to the die distribution, that value of x will be less than 5. Okay? And we can do this in our heads. Let's see, the 6 outcomes are 1, 2, 3, 4, 5, 6. And so 1, 2, 3, 4 are less than 5, and that's 4 out of the 6 or 2 out of the 3 outcomes. So let's just make sure that works. And it does. Footnote, there's a few issues with probability. Sometimes it doesn't give you the answer, but most times it does. All right, let's take this the next step up and ask now not whether x is less than 4, but whether x is less than some symbol. And z has a definition lurking around, I believe. It didn't, but if it did, I would want to clear it. So let's just, for good programming hygiene, clear z. And now let's compute the probability that a value x drawn from, or an x distributed as, that's what that squiggle means, distributed as the die distribution, what's the probability that that value would be less than or equal to z? And so we get a piecewise function, so that if the floor of z, that is rounding z down, is greater than or equal to 6, then that probability is 1. That is, am I going to get a value less than 9? You bet. What if I have a number like 3.4? Well, this is the floor of 3.4, or the floor even of 3.9 is 3. And so the probability that I'm going to get a result that is less than or equal to 3 is the floor of z, floor of, let's say, 3.4, 3.9, that's 3, divided by 6. So it's 1/2 in that instance. So this gives us a formula. All right, we can turn that formula into a Wolfram language function, and I'm going to do that by saying, just calculate the probability that it's less than z. For reasons that don't need to concern you, I need to wrap that in evaluate. And now I'm going to say make that a function of z and call that function Cdf die. We'll learn in just a moment why I'm going to call it Cdf. But there it is. And I can now, in fact, plot this function over the range -2 to 8. and we can see that in these sort of in-between values, like 1.3, 1.7, the cumulative probability doesn't change because there are no rolls of 1.4 or 1.7. And similarly, we can see when it's 8, the probability of getting a roll less than or equal to 8 is 1. And if it's less than 1, the probability of getting a roll that's less than or equal to 1 on a conventional die is 0. Okay, so this function that I just built, what is the probability that a value drawn from the distribution will be less than some number, is a function of z, and I can do it for any distribution virtually. And it's called the cumulative distribution function of the distribution, which is almost always abbreviated as CDF. Okay? So the CDF is the probability of a value drawn from the distribution being less than or equal to some number. So just for example, what is the CDF of the, let's say we've studied the uniform distribution. Let's do the discrete uniform distribution. We've seen that before, defined on the interval 1 to 6. What's the probability that it will be less than or equal to 5? And I hope you're able to know before I evaluate this that it's going to be 5/6. Okay, great. So we now have its concept of a CDF of a distribution, that we can have a function of something that is itself a function. Now let's look at another kind of function. Supposing I want to compute the probability that some x is not less than some value z, but that it's in between that value z and z plus some little value delta, and I'm going to divide that result by delta. And I'm going to restrict myself to situations where delta is a positive number. So let's actually do that on the log normal distribution. I know we haven't encountered the log normal distribution, but it's fine. It's just a firm. And if you were curious what the domain of that firm was, what kind of numbers can it output for even any arbitrary parameters a and b, it's a 2-parameter distribution, it can output anything from 0 to infinity. So let's actually look at this expression here. I'm going to say, what's the probability that the value x drawn from the log normal distribution is between z and z plus delta? And I'm going to divide that probability by delta itself. I'm also going to need to tell the Wolfram language that we should assume that z is positive, otherwise we start to get very strange things because the domain of the distribution is positive. And I'm also going to remind the kernel that delta has to be greater than 0. Okay, so we do this and we get this kind of icky expression, but if we look at it for a moment, it's some function erf, and its parameters are a, z, and b, the parameters of the distribution, and the value z, and how wide our interval is, delta. All right, so now what I want to do is I want to say, let's make delta as small as possible. So we're going to shrink the delta in the denominator, which may result in the denominator getting smaller, but we're also going to shrink the delta in the numerator, and maybe this will result in the numerator getting smaller. And so the question is, what's going to be the limit of that quotient as I start to get delta smaller and smaller? All right, so this might take a moment. It's thinking. All right, and we now have an expression that is free of delta because we've basically shrunk delta down to 0, and here it is, okay? You don't need to understand what this formula is, just understand that it is the limit as delta goes to 0 of the differences, or the probability that the value x will lie between two values z and z plus delta. So there's actually a name for this process of finding the probability that it will lie between two intervals and then dividing that by the size of the interval. That's called the probability density function, or the PDF. And so here, rather than going through all that limit stuff, I'm just going to ask Wolfram Language directly, hey, what's the PDF of the log normal distribution parameterized by A and B, evaluated at z, and let me just remind you that z is greater than 0. So if we do this, we get this expression, and if you stare at this expression and this expression, you'll see that they're the same. Okay, so the good news is that you don't really have to do all this limit stuff when you're actually using these functions. You simply have to understand what those functions are. And so in this handy-dandy chart, which I'm about to create, you're going to see a whole bunch of functions of distributions, okay? So we just covered the CDF. That's the probability that an output from the distribution will be less than or equal to some value. CDF has its sort of reverse, which is called a survival function, which is that the probability that an output from the distribution will be greater than some value. And let's look at two properties for the moments of CDFs. One is that it has to be between 0 and 1 inclusive. You could never have a probability of something being less than 0 or greater than 1, and it can never go down as the value gets greater, because as the value gets greater, either no more numbers are included or more numbers are included. You can never subtract. And so if you see a function and it's going down, you know, wait a second, that can't be a CDF. Survival function has the opposite property. It can never go up, because as you make tougher and tougher demands on the function, it can never produce more. All right, quantile is the inverse of the CDF. The CDF is some function, and you can take the inverse. That is, you can ask for what domain value is it true that the CDF is equal to 0.8. And so I can say, what is the quantile of the distribution at 0.8? And it will spit out an answer. Sometimes, by the way, the quantile is in fact called the inverse CDF. The mean. You can take the mean of a distribution, and this is, if you draw enough numbers, what is the arithmetic average of those draws? We have the PDF, which I just described, which is the limit as delta goes to 0 of the ratio between the probability that an output from the distribution will be between some value x and some value x plus delta. That's our numerator, and our denominator is delta. For discrete distributions, that is distributions that can only take on a finite number of values, then it's just the probability that you get that value. It's a much simpler computation for discrete variables. By the way, a lot of people call the PDF of a discrete distribution a PMF, or a probability mass function, but Wolfram Language does not. Okay, rarer probability. Rarer probability is, supposing you say, I want to look at the domain value 0.7. Okay? That has some PDF value associated with it through the PDF function. And I want to know what fraction of all possible values drawn from the distribution will have a probability less than the PDF of the number that I suggested. This is called rarer probability. It's only occasionally used in sort of conventional statistics, but it is used a fair amount in machine learning, so we will see it again. The hazard function. The hazard function is a function of a function of a function. That is, it's a function that looks at the ratio of the probability density function to the survival function. It's basically asking the question, hey, if you think of probability distributions as lifetimes, what's the probability you're going to live to 70? What's the probability that you're going to live to 80, etc.? The hazard function is the probability that you're going to die at a certain point in time, given that you've lived up until that point in time. So actuaries and the like love hazard functions. Median. Median is the value such that half the time a random draw from the distribution will be below that value, and half the time it will be above, and there are intriguing methods of dealing with ties. Central moment, I think I'm going to skip for the moment. Variance is you take the mean value of the distribution, you take the difference of each value drawn from the distribution between that mean and that mean, that gives you some positive or negative number, you square it, and then you take the mean of those squares, more or less. And so that's the variance. It's a measure of the spread of the distribution, and the standard deviation is the square root of the variance, with this footnote that there sometimes needs to be a correction factor. All right, so that is our chart of distributions. Let's look at each of these in some additional detail. First, let's look at the operation of the Cdf function and see how that's working. So we just take the Cdf of the die distribution evaluated at 5. We're asking what's the probability that a draw from the die distribution will be less than or equal to 5, and we get 5/6. We can look at a plot of the Cdf values as the argument goes from 0 to 7, and we see that at 0, the probability that you're going to get something that's less than or equal to 0 is 0. At 7, the probability that a roll of a die is going to be less than or equal to 7 is 1, and it has these interim values in between. For a continuous distribution, like the normal distribution, we don't want a discrete plot. We want to know the plot at all of the values of the domain. And so here we can show it over -4 to 4. Notice that it's bounded at 0 and 1, can't be less than 0, can't be greater than 1, and that it never goes down because a Cdf can never go down. We can do the same thing for a log normal distribution. If you scale the x-axis logarithmically, as I'm showing here, where it's kind of compressed on this end, you can see that the Cdf of a compressed log normal distribution looks a lot like that of a normal distribution, and that's because of the particular way in which the log normal distribution is defined. Okay, so we've seen a Cdf. What about a survival function? Survival function is sort of what's left after you have the Cdf. It's 1 minus the Cdf. It's the probability that a draw from a distribution will be greater than an argument. So here we're asking, what's the probability, given that you're having a draw from the die distribution, that its value will be greater than 5? Not greater than or equal to 5, but greater than 5. And the only number on my die that's greater than 5 is 6, and that's 6 possibilities. So the probability is 1 in 6. Just as a note, programming note, if you leave out a second argument to one of these things like survival function or Cdf, it will give you a function that will return answers in the future. So here I'm going to compute the survival function of the die roll, and you can see it's just a function. You can ignore the listable thing. We can make a discrete plot of the survival function, and you can see it's kind of the reverse of the Cdf. We can look at the survival function of a continuous distribution, such as the normal distribution. You can see it's bounded at 1 and 0, and that it never goes up. And you can see in this little piece of code that if I sum vertically the Cdf with the survival function, I always get 1, and that's essentially because they're defined so that they always equal 1. So what does it mean when you say, oh, I'm in the top 20% of my class? What that really means, and what you should now say from now on, is that the survival function of the grade distribution at the University of Houston Law Center, evaluated at my GPA value, is 0.2. So I suggest you try that in your next job interview and see what happens. You could ask, by the way, what does it mean? Supposing a job interviewer comes to you and they say, the value of the survival function at my school of the grade distribution evaluated at 3.14 is 0.35. So figure out what that means in case you ever interview someone for a job who's taken my course. All right, so what about the quantile function? The quantile is just the inverse of the Cdf, and sometimes we can use algebra to derive it. Here I'm basically saying, consider this logistic distribution. Don't need to know what that is for now, but it's another kind of distribution. And I'm going to say, okay, for what value of, given a y, for what value of x is this true? I'm solving for x. I get this function here, and that is the mathematical expression as a function of y for the quantile function of the logistic distribution with first parameter 3 and second parameter 7. If that seems a little bit abstract, maybe this will help. Let's make a parametric plot where we let x go from negative 40 to 40. We let our x coordinate be x itself, and we let y be the CDF coordinate. So if we do this, we just get the CDF of the logistic distribution. But what if we reverse the order of the coordinates? What if our x coordinate is the y value and our x coordinate is the x value? So we flip the order of the coordinates. That's one way of thinking about an inverse function. And so now when we do this parametric plot, we get something that looks like this, which looks remarkably identical to the quantile function of the logistic distribution. And so this should geometrically reinforce the notion that the quantile function is simply the inverse of this CDF. And so if you ask the question, hey, what GPA is it going to take for me to be in the top 20% of my class? That's really a quantile question. And what I hope you realize is from now on, you just do the following. You just say quantile GPA dist. And I'm asking top 20%, so I'm going to evaluate it at 0.8. Okay? So now you know about the relationship between GPAs, quantiles, CDFs, etc. All right, what's a PDF? Okay, so the first thing to know is that some people in literature will call the probability density function for a discrete distribution, they'll call that a probability mass function, abbreviated PMF, but Wolfram language uses the same technology or terminology for both a discrete and continuous distribution. So here's the PDF of the die evaluated at 3. Why is it 1/6? Well, it's 1/6 because there are 6 possibilities and all of them are equally probable. Or I can say, hey, let's make a plot of the PDF of the die function evaluated at from 0 to 7. What's the probability you're going to roll a 0? 0. What's the probability you're going to roll a 7? A 0, but for everything in between, it's equal. Okay, what about categorical distributions? I think I've mentioned those before. These are distributions that don't produce numbers or things that can easily correspond to numbers. They produce just discrete things, like maybe eye color or something. I guess no one has red eye color. Hair color. So we can ask, what's the PDF of this categorical distribution evaluated at green? And looks in its little table and it says, oh, the probability of green is 0.6. So I will just spit back 0.6. Now, can you compute the CDF of a categorical distribution? And now, first of all, I'm going to show you that Mathematica cannot do that. It just spits back what you gave it. And the reason it fails is that the concept doesn't make any sense. A categorical distribution just has things that come out that don't necessarily have any ordering to them. So we can't really say what's the probability that you'll get a value less than or equal to green, because we don't know if red is less than or equal to green or blue is less than or equal to green. What they do have, though, is rarer probabilities. And so what we're asking is, here, the probability of being blue is 0.3. So what's the probability that a random draw from this distribution will have associated with it a probability less than or equal to 0.3? And it's, well, blue makes the cut, it's less than or equal to 0.3. Green fails, it's 0.6. And red succeeds, it's less than or equal to 0.1. The sum of 0.3 and 0.1 is 0.4. And if I wanted to program that and we didn't have a rarer probability function, I could do this. But thankfully, we do have a rarer probability function. And so I can now just ask it. If I want to know what's the probability to be less than or equal to green, everything's less than or equal to green, and so it's 1. You might think this is awfully obscure, but it will come back when we talk about, for example, the Fisher test for categorical distributions. So it is not a totally useless concept. By the way, here's a visualization of rarer probability. Supposing we have a mixture distribution, meaning it's a certain percentage, it's 60% from this, 60% of the time you'll get a draw from this, and 40% of the time you'll get a draw from this. So we can plot that distribution's PDF. And now, supposing I want to know, I draw 6, and I want to know, hey, that seems kind of like a weird outcome. What's the probability I would get a value less than or equal to 6 if I were drawing from this mixture distribution? And so we can see this geometrically. Here I've shaded in red all the domain values for which the associated probability is less than or equal to it is at 6. And if one added up all of these areas, the red areas, and divided it by the area of the whole thing, you would get the rarer probability. Okay? So sometimes I am sloppy and sometimes other people are sloppy, and I say exchange PDF and probability. And while that's permissible for discrete distributions, it's not a good idea at all for continuous distributions. That is, let's evaluate the PDF of the normal distribution at 1.5. Okay, so we do that. We get some number, 0.129518. Can I say that the probability of getting a 1.5 is 0.129518? And the answer is no, you certainly cannot. There are a lot of ways to see this. One way would simply be to ask, hey, what's the PDF of the normal distribution of 0, and we'll make it have a very small standard deviation evaluated at 0.01, for example. And we're getting, it's 3.97. But you can't have a probability that's 3.97. It has to be between 0 and 1. And so a PDF is not, for a continuous distribution, the same as a probability. Sometimes we can call it a likelihood, but it's not a probability. All right. And you should know, as I think I mentioned in one of the annotations, for continuous distributions, the PDF is simply the derivative of the Cdf function. Let's look at the hazard function. I'm going to plot the PDF and the survival function of a distribution on the same graph. Here the distribution I'm dealing with is the uniform on the range 3 to 7. I'm going to plot its survival function and its PDF, and there you go. Okay? The blue is the survival, it's going down. The PDF is constant. Now I'm going to compute the ratio of the PDF to the survival function. And I get a picture that looks like that. That picture has a name. That's the hazard function of the distribution. It is the ratio of the PDF to the survival. And if you think of it in actuarial terms, it's the probability of your dying in the next instantaneous period of time, given that you were alive, that you actually survived. These are how many people are left. These are how many people die. And so this is essentially the probability, the instantaneous probability that you're going to die in some sense. Okay? So, or in Wolfram language, you don't have to actually do the division. You can simply say, could you please just plot me the hazard function? And there it is. All right. Maybe take a break here. I'm going to take a break, and we're going to come back, and we're going to look at conditional distributions. Let's take a quick look at conditional draws from distributions. So supposing you've got a uniform distribution on the interval 3 to 7, but you're told that the output is greater than 4. You might want to ask, well, now, what's the probability that it's less than or equal to 6? So when you see a question like this is really about a conditional distribution where you're constraining the domain, and we can write this in Wolfram language as follows. We can say let x be distributed according to the uniform distribution on 3 to 7. And we want to know what is the probability that x is less than 6, conditioned on, that little bow is a conditioned on. Sometimes you'll see it in other text with a vertical arrow, but Wolfram it's sort of a bow, given that x is greater than 4. So if I execute that properly, we get that it's 2/3, okay? And if you think about it, well, let's see. The numbers that are greater than 4 are 5, 6, and 7. 5 and 6 are less than 6, so there you go. All right, and we can also create a symbolic probability that a draw is coming originally from a certain distribution, but we're going to constrain the outputs in some fashion. So what's the probability that x is less than or equal to 1, given that x is greater than 5, and we're drawing from a normal distribution? And we get this very complicated expression here for what the conditional probability is. Now it's time to look at joint and marginal distributions, which apply really only to multivariate distributions, things that produce more than one output at a time. So it might produce an x value and a y value simultaneously, or if it were a categorical distribution, it might output a eye color and a handedness simultaneously. So we're going to use binormal distribution to create such a distribution. It's has means of 1 and 4, standard deviations of 1 and 2, and the correlation between its x output and its y output of 2/3. So we'll just do that, call it multi, and now let's use plot3D to show the PDF of a multivariate distribution. So we're going to let x go from -3 to 5, y go from -1 to 8, and you can see it's sort of this hill here. There's a picture of our distribution, the PDF. We can see what it outputs. Let's ask it. Random variate is the command that says, hey, let's see produce factory. So I want you to produce 10,000 of them. There they are. We only see a few of them. The rest are elided, thankfully. But we could ask for a histogram of a sampling from this, and you can see that the picture of the sample looks roughly like the picture from the actual PDF that we saw before. So again, we could ask questions about this. We could ask, hey, what's the probability that a random variate drawn from this will have an x value greater than 2 and a y value greater than 5? So we're sort of asking about the cumulative probability of being in this zone here. I can use survival function to do that. The n, as you may recall, just says get me the numeric value of it. And it turns out that has an 11.7% probability. All right, that's joint distributions very quickly. Let's talk about marginal distributions. Marginal distributions are where you kind of collapse some of the dimensions of the distribution. You say, for example, here, I don't care what the y thing is. I just want to know what are the distribution of the x values. Or, I don't really care about the x values. I just want to know what's the distribution of the y values from this joint distribution. And when you ask a question like that, you're asking about marginal distribution. So here we can sort of fake a marginal distribution. We could ask on how many occasions in our 10,000, is that what we drew? 10,000 draws from our binormal distribution. On how many occasions of that would the x value be greater than 2? So it's asking, in Wolfram language, count all the examples here that match this pattern, x, y, where the x value is greater than 2. All right. So, turns out it's 1,548. And so one thing we could do is now write a table that said, hey, for some value of z, I want you to tell me on how many occasions the x value is greater than z. And then I want you to divide that by 10,000. All right. So it did that, and we could plot that. And what does this look like? Well, it looks like a survival function. It's going down, starts at 1, ends at 0, and indeed that's what it is. It is the survival function of the first marginal distribution of our joint distribution. First, because we're looking at the x value, which is first in our coordinate list. We could also do the same thing, find out when the y value is greater than some value z. We'll make a table. Done. And now we will list line plot that table, and we have our y marginal. And so really what I just did is sort of a crude way, a simulated way of getting the marginal distributions. Or Wolfram understands, hey, there are better ways of doing this, And so you can ask for the first marginal of the distribution and the second marginal of the distribution. And it's not a coincidence that the first marginal has a mean of 1 and a standard deviation of 1, and the second marginal has a mean of 4 and a standard deviation of 2. And so there's a relationship between the marginal distributions and the joint distribution. We are going to see marginal distributions and conditional distributions again when we look at Bayes' law, which some people think is the most important concept in statistics, and I might in fact be one of them. So this is why I am introducing you to conditional draws, marginal distributions, joint distributions right now. Onwards, let's look at transformation of distributions. Okay, so far we've looked at the distribution just produces an output, but nothing ever happens to the output. Okay, there's no quality control on the output. Truncated distribution is, you could think of as a form of quality control, that if the result isn't between 0.9999 and 3 on our die, we don't want it. Okay? So you might ask, well, given that you've rejected anything outside of this domain, what does the distribution look like that's left? What's the probability of, say, drawing a 2, given that you have rejected 1s, 4s, 5s, and 6s? And so in this case, it's not very hard to figure it out. It's the uniform distribution, discrete uniform distribution on the interval 1 to 3. You could also say, hey, I'm starting off with a normal distribution, but quality control, they say if it's less than 1, we don't want it. Anything greater than that's fine. That's why we've truncated at infinity. And let me see 20 draws from that. And you'll see that nothing that's less than 1 gets out of the factory. Okay? And so one thing we could do is to see what does the PDF of a left truncated normal distribution look like as we vary the truncation point. So I'm just going to draw my left truncation point across here. And you can see that even though we start out with a normal distribution, we end up with something that doesn't really have a little bell. It's sort of going up to a bell and then dying out. So that is a truncated distribution. It's often useful, supposing that I have a bunch of applicants to law school. They have LSAT scores. And I know that we will, and here's what our distribution looks like. This is what the applicant pool looks like. Assume it's a normal distribution with a mean of 147 and a standard deviation of 14. But we basically only draw from the 152s to 164s. And so I might want to know, hey, what does the distribution look like of our applicant pool? So I'm going to form a truncated distribution, truncating over our interval based on our original distribution. And now I could plot the PDF of that distribution. I'm going to plot the PDF of the overall pool and the PDF of our people that we might admit. And so you can see that there's a distinct difference between those two distributions. So what kind of problems can we solve using the idea of a truncated distribution? Well, let's see. Okay. We can compute the mean. Okay, we can ask, hey, if we don't take people with below a 152, what would, and here's our applicant pool, what's the mean of those who remain? And it's a 161. But what if applicants with LSATs over 164 refuse to come to this school? Not good enough for them. Well, we could then ask, okay, let's truncate the bottom at 152, but let's truncate the top. Let's right truncate at 164. Let's compute the mean of that, and I just want a number, so I'm going to do a postfix n on it. And after a moment, it's going to tell us that we've got a mean of 157, just out of curiosity. because I can't help wondering, what's the median of this? Because that's in fact what US News would care about. So let's see here. All right, well, that's not very helpful. I'm going to use the suggestions bar, which is telling me, don't you think you want the numeric value? And it's a 157.051, not that much different. And so you could see our dean or admissions staff fiddling with these cutoffs and trying maybe to have scholarship, so the 165s will come, all to get our mean LSAT up. But in any event, in fact, here's a question that I ask. Supposing you want the median LSAT to be 160, where do you have to cut, assuming, by the way, here I'm not doing the applicants greater than some value refuse to come. And so find root is a way of trying to find when some expression is 0. So I'm basically saying when is 160 minus the median 0? And I'm going to make an initial guess of 154. And it turns out that the cut score I need is 156.853. And actually, of course, you know that really can't be, because cut scores, you can't get an LSAT of 156.853. Anyway, if you want to have some fun, try to model this as a discrete distribution problem. But for the moment, I hope that you understand truncated distributions. It's a form of quality control. You can think of censoring as a different form of quality control. Instead of just rejecting the sample, you fix it. And you fix it in a particular way. If it's greater than the censoring number, the right censoring number, you reduce it to exactly the censoring number. So let's see an example of this. Supposing we have a lawsuit and the distribution of damages is thought to be distributed in a log normal distribution, and the mean of that log normal distribution is $200,000 and the median is $140,000. So we could compute the mean amount of damages, and if we didn't think some more, we might say, well, if a settlement offer comes in at, say, $175,000, that's worse than the average. We should probably reject it. But what if the defendant has a net worth of only $300,000? And so if the random judgment factory produces a judgment of $500,000, I still really only get $300,000 because that's all there is. So what I want to know is the mean of collectible damages. And so what I need to do is fix all the outputs that are greater than $300,000 and make them $300,000. The transformation that does this is called a censored distribution. I'm going to censor it, left censor it at negative infinity. I'm not going to bother with that, but I am going to right censor it at $300,000. So, and now if I take the mean of that, I get $159,636. So maybe I should accept that offer of $175,000, because if I take the defendant's net worth into consideration, the settlement offer is better than that. Okay, so far I've just looked at a few transformations of distributions, but you can have very general transformations of distributions. So for example, the idea here is you have the output from the random family generator factory, and then we do something to it. We do something deterministic to it. So here we have our output drawn from the normal distribution firm, factory 0, 1, and we take that output and we transform it by taking it, using that to exponentiate e, that 2.718 number. And so if we do that, we actually get a named distribution. That is the log normal distribution. That's, in a sense, the definition of the log normal distribution. It is the transformation by e to the x of the draw x from a normal distribution with mean of 0 and standard deviation of 1. And by the way, you can reverse it out. If you take the log transformation of the log normal distribution, you get back the normal distribution. And in fact, there are lots of people who've made these beautiful pictures showing all the relationships among the distribution families and how you get from one to another. All right. By the way, you should know that although in the instances I just showed you, when you do the transform, there's actually a named distribution that results. Oftentimes you don't get a named distribution. It's just what's the transform distribution of multiplying the output from a beta 1, 2 by 5? Well, it's just the transform distribution of multiplying by 5 of a draw from a beta distribution 1, 2. The notebook points out a way of going from one transformation to another. I think that's probably just best read and not have me comment on it here, so that I can move to the expectation operator. And the idea of the expectation operator is, I don't want the mean of an underlying distribution. I want the mean of some transformation of the distribution. And when we do this, it's called taking the expectation of the transformation function with respect to the distribution. So supposing I want to know what is the mean of a draw from the normal distribution transformed by squaring it. So I could say, what is the expectation of x squared where x is subject to the normal distribution on 0, 1. And if I do this, I get 1. And if I do this, you get 1. It's exactly the same thing. Okay? So I ask here, can you compute the expectation of the cube of rolls from the die distribution? So let's see if we could do that. Expectation of x cubed, where x is distributed not according to the normal distribution, that doesn't simulate die rolls, but the discrete uniform distribution on the interval 1 to 6. And if I do that, it turns out it's 147 over 2, which is 73.5. Okay? Here's another thing I could do. I could ask, what's the PDF of we take two distributions? One's a die, the other's a die, and we add them together. So this is like if anyone still plays Monopoly, you have two die, you roll them, and you go as many spaces as the sum of those two die. And so let's see what the probability is of getting a 6, and it's 5/36, and we could do lots more with that, but I will leave that as an exercise for you. I just want to conclude this long talk with some probability facts, and I'm hoping some of you knew these before you took the course, but anyway, if you didn't, here they are. Probabilities have to be between 0 and 1, can't be bigger than 1, can't be less than 0, and if two events are independent of each other, to get their joint probability, you multiply their probabilities together. So if the probability of a person being left-handed is 0.3, and the probability that they have type A blood is 0.4, and handedness has no correlation with blood type, then the probability that I am both left-handed and have type A blood is 0.12, and you should know that if the events are not independent, that is, supposing it's the case that left-handed people actually tend to have more type A blood than right-handed people, then you can't do the straight-out multiplication. There are some correction factors that need to be applied. And that concludes our discussion of basic statistics. We're going to be using this throughout the course, and so I want to make sure that you have a good foundation.